Welcome, dear students, to this part D of lecture 1, where we are discussing the mathematical basis of finite element method. And in this part, we will discuss the formulation of finite element using Rayleigh-Ritz method. So, our outline today will be: first, we'll study what is principle of total potential or minimum total potential energy. And then actually this Rayleigh-Ritz method is based on minimization of total potential energy of a system. So we'll define what is total potential energy and then we'll minimize it. And this classical Rayleigh-Ritz method, which is again another method of finding approximate solution of partial differential equation or differential equations, just like Galerkin's method. So we will take up a small illustrative example illustrating the use of classical Rayleigh-Ritz method, how it is used, and then we will cast this method in the finite element form. And to do that, we will formulate our familiar two-noded bar element using this Rayleigh-Ritz method. And while formulating this bar element in this class, we will study or we'll see what is natural coordinate, and then we'll also learn what is isoparametric bar element, and then we'll formulate the element stiffness matrix by using this Rayleigh-Ritz method. And of course we can also find out the nodal load vectors in this method once again. So now let's start. Now, what is principle of total potential energy? First, let us see what is total potential energy. Total potential energy, okay, total potential energy So we define the total potential energy as the strain energy in a system, strain energy stored in the system, minus the work done by the external loads, work done by external loads, over the displacement field that the system is undergoing. Okay. So, for example, we know the strain energy of bending, we know the strain energy of axial deformation, etc. from your structural mechanics knowledge. You know their formulae. So, when we subtract the strain energy stored by the internal work done, that means strain energy is what? The internal work done by the stresses and strains, okay, within the body. And when I subtract from that strain energy the work done by the external loads, then whatever we get is called the total potential energy, TPE. Okay. Actually, by convention, we define the work done by external loads as negative quantity. That's why effectively we are summing up the strain energy and the work done by the external load. Okay. And we usually denote this total potential energy by capital pi, and this capital pi is actually the sum of strain energy, which is denoted by capital U, plus negative of this work potential W, where this U is my strain energy and work potential is the work done by whatever load the system is acted upon by. Okay. Now let us see what is the principle of minimum potential energy. Principle of minimum potential energy. So this principle says that if I have a conservative system and the system may undergo, suppose I have a cantilever beam, say, okay, and it is acted upon by some load, some arbitrary load, and it may undergo some deformation. The deformation pattern we do not know right now, but we have to fulfill a kinematically admissible solution, kinematically admissible deformation field we need to consider. So what is kinematically admissible solution? We have already used this in Galerkin's method. So an admissible solution will be fulfilling the essential boundary conditions, and also it will be continuous enough so that there is no discontinuity in the deformation within the body. Okay, and when we have that kind of a displacement field or displacement function, then we will call it admissible solution, kinematically admissible solution, or kinematically admissible displacement field. Now, the principle of minimum potential energy says that for conservative system, if I have a kinematically admissible displacement field, then those kinematically admissible displacement fields will extremize the potential energy. And whenever that extremum is a minimum, that means whenever my potential energy, total potential energy for a particular admissible displacement field or assumed solution is minimum, then that will lead to stable equilibrium of the body. Okay, stable equilibrium of the body. So what we can write then, suppose I have many displacement fields, say U. Remember, this is small u, so it's a displacement field. Capital U is used for denoting strain energy. So these displacement fields, I may have many possible displacement fields. Out of that, if the displacement field which is in stable equilibrium, if that is say U star, then corresponding to that U star, whatever is my potential energy total potential energy pi, okay, that pi will be minimum. So this is meant by principle of minimum potential energy. And in terms of variational calculus, this says that if I give some variation to the potential energy, that variation will lead to 0, provided if and only if my u is corresponding to my u for stable equilibrium. The displacement field corresponding to stable equilibrium, that only will lead this variation of potential energy to be 0. That means the potential energy will remain same or stable for small change in displacement field. So this potential energy is also called a functional in the terminology of variational calculus. We call function of a function as functional. Since I know that displacement is a function of the spatial dimension, say because this is a one-dimensional structure, I know that u is a function of ux, and this potential energy is a function of u, okay, at least the strain energy is a function of u, so potential energy is a function of u, and that's why this potential energy is actually a functional. This potential energy is a functional, and if I have a functional whose variation is 0, then as per the principle of minimum potential energy, we can say that that potential energy corresponding to the displacement field which is generating that potential energy, that must be the stable equilibrium displacement field. That means that is the true displacement field. True means it doesn't mean that it is exact displacement field, okay? Because Rayleigh-Ritz method is an approximate method, all right? So here I can write that this u star is my displacement field for stable equilibrium. Okay, by using this principle of minimum potential energy, we can find out, just like Galerkin's weighted residual method, we minimize the residual. Here we minimize the total potential energy to get the approximate solution. Okay, so this is the basis of Rayleigh-Ritz method. Now let us take up an example, very simple example, to illustrate the use of Rayleigh-Ritz method in its classical form, all right, in its classical form. Now for illustration of this classical Rayleigh-Ritz method, let us take this example. We have a simply supported beam. It is hinge support. It has a hinge support at left end, and it has a roller support at the right end, and we take x equal to 0 here, and the x increases towards the right hand side, and the length of the beam is L. The beam is a prismatic beam, so EI is constant. EI is constant. Its span is L, and it is acted upon by a UDL of intensity Q, say. Okay. Now, like in Galerkin's method, here also we first assume an approximate solution for the problem. That means we will assume an approximate form of deflection, which we do not know. Our job is to find out this deflection. Okay. So, since we know that it is some kind of a parabolic deflection curve is somewhat parabolic, therefore let us take up a quadratic solution. Okay, let us assume a quadratic solution, and we are calling this deflection as V, which is a function of x. So let us take, say, let V of x, it is a quadratic polynomial, so we are taking a0 plus a1x plus a2x square. Okay. Now let us apply the essential boundary conditions. What are my essential boundary conditions? We know that at x equal to 0, V is 0, and at x equal to L, again V is 0. So therefore, V at 0, if this left end is, say, A, and say this is my point B, and say the midpoint is, say, C. Let me call it C. All right. So V0 is equal to deflection at A, that means equal to 0. So this means what? My A0 will be 0, isn't it? Because when I put x equal to 0 in this equation, my A0 is 0. All right. Similarly, by using the other EBC, so EBC, let me write it. The other EBC is that VL is equal to 0, and this gives me, I know that A0 is 0, therefore A1 into L plus A2 into L square is also equal to 0, right? And therefore what I get A1 is equal to minus A2 into L, right? If I take A2 towards the right hand side and divide both sides by L, I get A1 equal to minus A2L. And now I can use these values in the approximate solution, and then what I will get? I'll get therefore V of x is my A1 into x, so minus A2L x plus A2 x square. Okay, so we have now only one unknown coefficient, that is A2. All right, I can also of course simplify this as A2x into x minus L if I want. All right, so this is one equation. So we have expressed my displacement in terms of a quadratic curve having single unknown. Now what we do, let us now find out the total potential energy of the system for this displacement field Vx. Okay, so now total potential energy is what? Pi, capital Pi is equal to capital U minus W, where U is my strain energy and W is my work potential. That means it is the work done by the external load over the displacement field. Okay. So now, from our knowledge of structural mechanics, we know that potential energy for bending is given by half of EI, then second order derivative of the deflection, square of that, and this thing integrated over the whole length. Okay. And so, since our beam is having a constant cross section and material type is same, therefore this EI is constant, so we are taking it out. So EI by 2 integration of V double prime x whole square dx, where V double prime means second order derivative of V. Now earlier we have got Vx as a2x square minus a2lx. So from there we can find differentiation, first order differentiation, v dash x as a2l minus a2l, you see here, minus a2lx, differentiation of this will give me minus a2l, and then twice a2x. Okay, and therefore my v double prime will be twice a2, and hence my strain energy of bending will be given by EI by 2 into twice a2 square dx, and it's a straightforward integration, so I will get directly this 4, it will be 4 by 2 is 2 EI a2 square into L. Okay, so we have the strain energy of bending for the beam for our problem is this. Next, let us find out the work potential. So what is my work potential? Now work potential is W, that is the total work done by the loads over the displacement. So I will have to integrate this Q times Vx over the length of the whole beam. Okay, and therefore my work potential will be integration of 0 to L Q into Vx dx, right? And we know what is my Vx. My Vx is, by putting the value of Vx, this let me put it here, this will be 0 to L. Q is a constant, so I can take it outside, Q, and my Vx was a2x square minus a2lx. So a2x square minus a2lx dx. Okay, and this gives me Q into A2 into 0 to L x square dx minus q a2 L into integration of 0 to L x dx, and this means I get q into a2 into this will be L cube by 3 minus q a2, this will be L square by 2, so L cube by 2, okay, L cube by 2. And so I can further simplify it, qa2 into L cube into 1/3 minus half, and 1/3 minus half is how much? So qa2 L cube into, this is my 6, so 2 minus 3, so minus 1, so minus 1 by 6, and therefore my W is minus qa2 L cube by 6. Am I right? So, okay, this is okay. So now what is my total potential energy? So TPE, which is pi, capital pi, is my U minus W. So U was how much? U was twice EI A square L, twice EI A2 square into L, and minus, so minus minus plus Q A2 L cube by 6. Okay, so this is my value of pi. Now from the principle of minimum potential energy, what do we know? We know that, so based on principle of minimum potential energy, PMPE, we know that del pi del A2 is 0. So let us find out partial derivative of this quantity with respect to A2. So therefore del pi del A2 is, I have 4 EI into A2 into L plus Q L cube by 6, and this is equal to 0. Okay, and hence from here what is the value of A2? So A2 will be, I can divide both the sides of this by L. In that case I will have L square only, so A2 will be minus QL square by 24 EI, right? 24 EI. So this is what is my value of A2, and therefore now I can write what is my Vx is this a2x square minus a2lx, or a2x into x minus l, a2x into x minus l. So a2l into x minus l. So therefore my Vx is a2x into x minus l. All right. So now once I got the value of a2, we had a quadratic equation, so a1 and a2 are there. Therefore, what is my Vx? My Vx was a1x plus a2 into a1x plus a2 into x square. So yes, this is my Vx. I'm okay. a2x into x minus l. And therefore my Vx is this ql square into x minus, okay, let me put it. So Vx was my a1x, so a1 is minus a2l, so minus a2l, so minus a2l into x minus a2 plus a2 into x square. So minus a2l will give me ql cube by 24 ei into x minus a2 x square. So ql square by 24 ei into x square. And now I can take ql square by 24 common, ei common, so ql square by 24 ei, then I have xl minus x square. Okay, so this is my value of the deflection at any point x. So my deflection at the midspan will be x, value of x is L by 2, so I'll put the value of x as L by 2, so it will be L square by 2 minus L square by 4, so it will be QL square by 24 EI into L square by 4, so it is QL to the power 4 by 96 EI. Okay, so central deflection is this QL to the power 4 by 96 EI. Now from structural mechanics, you know the exact solution. If I have a beam of span L with loaded by a UDL of Q, then I know that the central deflection is given by 5 QL to the power 4 by 384 EI. And instead of that, this approximate solution has given me QL to the power 4 by 96 EI. So in place of 5 by 384, I have 1 upon 96 here. So the percentage error will be the exact value minus the approximate value divided by the exact value into 100%, and this will give me 20% error. So we have seen that if I take a quadratic displacement approximation, then I commit an error of about 20%. Okay, so this is how we can apply the classical Rayleigh-Ritz method to solve simple problems. Okay. Okay, let us take our next example. We will use the bar problem here, and the problem is this: we have a circular pile of length 10 meter. The diameter of pile is 60 centimeter, and it is surrounded by the soil having a cohesion of 50 kilopascal throughout the soil. We are assuming constant cohesion. That takes place in case of over-consolidated clay. In normally consolidated clay, usually cohesion increases with depth linearly. And then we take an adhesion factor of 0.5 for clays usually, so that the frictional resistance around the pile will be given by alpha into C. Okay, that is what is adhesion. And the pile is loaded by a 100 kilonewton load, downward load at its end, free end, and the bottom can be assumed to be fixed. Now our job is to find the elastic settlement of the pile under the column load. Okay, so it is again actually a problem of axial deformation of a bar. And now let us solve it. We are assuming M25 concrete. So from IS 456 I can have the E value of the concrete. Okay, and therefore now let us do the initial calculations before we actually go for the Rayleigh-Ritz method. So first of all, let us find out the value of E. Value of E as per IS 456 is 5000 root over FCK in Newton per millimeter square. So 25 will, square root of 25 will give me 5, so it is 25,000 megapascal. Okay, 25,000 megapascal, and that means my E will be how much? So this will give me E equal to, let us work in kilopascal unit, kilonewton and meter unit. So my E is 25 into 10 to the power 6 kilopascal. Okay, and my area of the pile is, the diameter is 60 centimeters, so pi by 4 into 0.6 square equal to, I have area as 0.28274, 0.28274 meter square. So the value of AE, it is always good to calculate the value of AE. So because I know that it will be required again and again, so AE is 7068.5 into 10 to the power 3 kilonewton. Okay, so these are some initial calculation. Then in Rayleigh-Ritz method we had used this surface traction as load per unit length, right? Load per unit length, because it is a one-dimensional structure. Therefore, this C into alpha I have to multiply by the perimeter of the pile so that I get the surface traction in force per meter unit. Okay, and therefore let me find Q. Q is alpha into C into pi into diameter of the bar. Okay, diameter of the pile, and this gives me 0.5 into 50 into pi into 0.6, right? And this gives me the value of Q as let me find out it. So this gives me 47.124 kilonewton per meter. This is my value of Q. Okay. Now let us use the classical Rayleigh-Ritz method. Let us take up a quadratic polynomial for the displacement function. So therefore let U x be a naught plus a1x plus a2x square. Now my x I take equal to 0 at the fixed point, just like the earlier bar, and it increases towards the pile top. Now I know that at x equal to 0 my u is 0, therefore u0 equal to 0 gives me a naught equal to 0, and hence I have u equal to a1x plus a2x square. Fine, a2x square. Now we know in Rayleigh-Ritz method what I will have to do. I will have to find out the total potential energy, and total potential energy will be given by strain energy minus the work potential. So now my strain energy for axial deformation is given by half of zero to L AE times u dashed square dx by this. Okay, this is my potential energy for axial deformation, and therefore now I can find out this by putting the value of u dashed. So what is my u dashed? So when I differentiate this, I get u prime as a1 plus twice a2 x, and therefore my u prime's whole square is a1 square plus 4 a1 a2 x plus 4 a2 square x square, right? And now when I put this value here, let me go to the next place. Then I get, therefore, potential energy is, since my AE is constant, I will take it out. AE by 2 into integration of 0 to L A1 square plus 4 A1 A2 x plus 4 A2 square x square dx. And when I do this integration, I get straightforward AE by 2 into, I'll have A1 square L plus 4 A1 A2 L square by 2, so it will be 2 A1 A2 L square, right, plus this is 4 A2 square L cube by 3, so 4 by 3 A2 square L cube. So this is my strain energy due to the axial deformation for the bar. Okay. And I can further simplify it because I have a 2 here, and therefore I have AE A1 square. Okay, let it be like this, or let me put it AE A1 square by 2 into L plus AE A1 A2 L square plus, this will be 2/3 2 AE by 3 A2 square L cube. So this is my U. Okay, let me mark it. So capital U is this. Next, let us find out the work potential. Now, work potential will be the total work done by all the forces over the domain. And now you see this, my force P is a compressive force, so it will be a negative force. Okay, so therefore I can now write the work potential. Work potential W will be given by integration of 0 to L Qx dx. Okay, minus this load is a concentrated load, so I will have P into U of L, because the deformation under the load is U of L, and therefore what I can write it as 0 to L Q into A1x plus A2x square. So I'll write A1x plus A2x square dx minus what is my UL? UL, let me write it here. UL is A1L plus A2L square, right? So this will give me minus P A1L minus P A2L square. Okay. So by integrating I get this will be my L. So Q A1L plus Q A2 L cube by 3 minus P A1L minus P A2L square. Okay. It is x dx, so L square by 2. Yes. So this is my work potential, and therefore my phi, that is total potential energy, will be U minus W. So U minus W is and this I will get as AE A1 square L by 2 AE A1 square L by 2 plus AE A1 A2 L square plus 2/3 AE 2 AE by 3 A2 square L cube minus this, so minus Q A1 L square by 2 minus Q A2 L cube by 3, then minus plus P A1 L plus P A2 L square, P A2 L square. So this is my total potential energy. All right. Now, from principle of minimum potential energy, what I know that variation of this pi with respect to A1 or A2 will be 0, and therefore, so principle of MPE gives me what? Gives me that del pi del A1 is 0 and also my del pi del A2 is also 0. Okay, and now therefore what is will be my del pi del A1? Del pi del A1 is from this term I will get twice A1, so that 2 and 2 will go, so AE A1L. First term will give me AE A1L. Then next term will give me plus AE A2L square, AE A2L square, right? Then I will have this term, so minus QL square by 2, so minus QL square by 2, and then plus PL, and this whole thing is 0. Is that right? And that means I need to solve for A1 and A2 from this equation. Therefore I will keep the terms containing A1 and A2 in the left hand side and take the other terms in the right hand side. Therefore I will have AE A1L plus AE A2L square is equal to QL square by 2 minus PL. So this is my equation 1. And then similarly del pi del A2 will also be 0. Similarly del pi del A2 is 0. This will give me what? This will give me this term will give me AE A1L square, AE A1L square, AE A1L square. Then next term containing A2 is 2/3 AE square L cube, so this will be 4 by 3 AE A2L cube. So whether it is plus or minus, it is plus. So plus 4 AE by 3 A2L cube, A2L cube. Then next term I have minus Q L cube by 3, so minus Q L cube by 3, and then PL square plus PL square plus PL square. This is 0, and therefore I will have AE A1L square plus 4 by 3 AE A2L cube is equal to QL cube by 3 minus PL square. So this is my equation 2. Now I need to solve these equations 1 and 2 for finding A1 and A2. Now this equation, everywhere there is L, so I can divide both the sides by L, and then I will get AE A1L plus 4 by 3 AE A2L square is equal to QL square by 3 minus PL. Let me call this as equation 2 instead of the earlier one. So if I subtract equation 2 from equation 1, then this term containing A1 will cancel, and therefore using equation 1 minus equation 2 gives me what? Gives me AE A2L square AE A2L square into 1 minus 4 by 3. 1 minus 4 by 3 is equal to QL square into half minus 1/3, half minus 1/3, and minus PL plus PL, so nothing will be there. P terms will not be there. Okay. No, this is minus and plus, yes, so it will cancel. So therefore now I can find out the value of A2 here. So again this L square will cancel, and therefore let me first simplify these fractions. This is 3 minus 4, so minus 1/3, minus 1 by 3 is equal to Q into half minus 1/3, so 1 by 6, right? 1 upon 6. So again, if I multiply both the sides by 3, then I'll have half here, and therefore my A2 is minus Q by twice AE. So this is my value of A2. Okay. So now this value of A2 we have got, which is minus Q by twice AE. Now let us put this value of A2 in equation 1. Equation 1 is this: AE A1L plus AE A2L square equal to QL square by 2 minus PL. In fact, I can divide both the sides again by 1L to further simplify. Okay. but let us ignore that now. So let us put this A2 in that equation. So AE into A1L is equal to QL square by 2 minus PL minus AE A2L square, right? So AE A2L square, AE L square into A2. This value A2 is minus Q, so this minus and minus becomes plus. So finally I get QL square minus PL. And therefore my A1 is equal to 1 upon AEL by QL square minus PL, or QL by AE minus P by AE, or 1 upon AE QL minus P. So therefore now by using the value of A1 and A2 in our original equation of X, which was original equation of U was A1X plus A2X square. So when I put that value, then I get U equal to A1X, so 1 upon AE QL minus P into X minus Q by 2 X square whole thing divided by AE. And therefore the deformation under the load I'll get by putting X equal to L. So when I do that, UL equal to 1 upon AE QL minus P into L minus QL square by 2, and upon further simplification we get this value 1 upon AE QL square by 2 minus PL. Okay, and therefore now using the value of AE and Q and L and P, we get this equation, and when I put these values I get these many meters, 0.000192 meter, that means 0.192 millimeter. So this gives me the deformation of the pile, elastic deformation of the pile under the load when it is acted upon also by this adhesive resistance of the soil, a constant adhesive resistance. Okay, so this is how we can use RR method to solve simple engineering problems. Of course this is an approximate solution, so there will be some error in the actual value of the deformation. All right. Next, we take up our familiar bar element once again, two-noded bar element, and let us find out its stiffness matrix, this time by using Rayleigh-Ritz method. Earlier we had done the same thing by using Gallatin's weighted residual formulation, and now we will be using Rayleigh-Ritz method, and we will see that both the methods give us the same result finally. So let us take up one bar element of length L. It has node 1 and node 2 at the ends. The node 1 is at location x1 and node 2 is at location x2, and my nodal degrees of freedoms are u1 and u2. All right. Now this time what we do, instead of defining everything in terms of the absolute coordinate, we define something called natural coordinate, which is a pure number, and this natural coordinate we denote here by xi, and xi is defined like this: xi equal to 2 by x2 minus x1 times x minus x1 minus 1. All right. Now let us see what happens, what are the values of xi at these two nodes. At xi, when x is equal to x1, we find this is 0, so I will have xi equal to minus 1, right? So we have written it here, at node 1 xi is minus 1. Similarly, when x is equal to x2, Then I have this becomes x2, so I get twice x2 minus x1 by x2 minus x1 minus 1, so this becomes 2. 2 minus 1 is 1. So the value of natural coordinate at the other end is 1. All right. And you can obviously make out that at center point it should be 0. Let us check whether it happens or not. So xi at midpoint, what is the value of x at midpoint? It is average of this x1 and x2. So it is x1 plus x2 by 2. And putting this value of x in the equation for xi, what I get? 2 times x1 plus x2 by 2 minus x1 divided by x2 minus x1 minus 1. And if I simplify, finally, I get that xi is 1 minus 1, that is 0. Okay. So now we can express any point within the element with the help of this natural coordinate xi. Okay. So it will depend on where it lies compared to the total length of the element, and accordingly I will get easily the value of xi. Okay. Now we have already seen the concept of shape function in Galerkin's method. Here also the same concept will be used. Now let us define the shape function in terms of the natural coordinate now. So that n1 I have defined as 1 minus xi by 2 and n2 as 1 plus xi by 2. Okay. And therefore, if I now want to express my displacement over the element in terms of the nodal displacements, that is what we always do for finite element formulation, because my nodal displacements are basic unknowns. So I will write ux equal to n1 u1 plus n2 u2, where in matrix form I can write it like this. This matrix, row matrix, into this column vector of nodal displacements, and this matrix I call transpose of n, so that n is a column vector of n1 and n2. And obviously my value of n1 at node 1 is 1, right? Because xi is minus 1 at node 1. Therefore n1 is 1 and n2 is 0, because 1 minus 1 becomes 0, numerator becomes 0. Similarly, at node 2 my xi is 1, therefore n1 is 0 and n2 is 1. So it is fulfilling those properties of shape functions, that it should be 1 at the node for which it is defined and 0 at all other nodes. Similarly, I also know that sum of the shape functions should be 1 at any point. So at a general point xi, I can find that n1 plus n2, n1 plus n2, n1 plus n2 obviously is 1, because it is 1 minus xi by 2 plus 1 plus xi by 2. So therefore I obviously know that this is half and this is half, so it is 1, and minus xi by 2 and plus xi by 2 will cancel, so this sum is 1 at any point. So all the properties of shape functions are now fulfilled by our shape functions. Okay. So therefore these are valid shape functions, so we can go for using this. Okay. Now let us do the coordinate transformation. This equation which expresses my displacement at any point in terms of the nodal displacement, this is called equation of displacement transformation. Let me write it. I have already written displacement transformation here. Okay. So this equation gives me displacement transformation. All right. Now similarly I can do coordinate transformation. So let us do that. So coordinate transformation. Coordinate transformation. Here what I will do, I will express the location at any point within the element in terms of the nodal locations. Okay. For that we come from the definition of xi. We have this definition of xi. So let us write it. So we have xi equal to, what was the value? Twice x minus x1 by x2 minus x1 minus 1. So from here, if I add 1 in both the sides, then 1 plus xi becomes what? 1 plus xi becomes 2 into x minus x1 by x2 minus x1. Okay. And therefore from here I can find out the value of x. So therefore x will be how much? x2 minus x1 into 1 plus xi is equal to twice x minus x1, right? So I have twice x minus twice x1. Let me write it like that. Twice x minus twice x1 is equal to 1 plus xi into x2 minus x1. Is that right? And from here what I get, therefore x will be 1 plus xi into x2 minus x1 divided by 2 minus x1. Am I right? And from here, if I now take x1 common, let us separate the x1 terms. So here I have minus 1 and here I have minus 1 times 1 plus xi, right? No, this should be plus, no? Because I have taken to the other side, so it should be plus. So I have therefore x equal to x1 times 1 minus 1 plus xi by 2, 1 plus xi by 2, and plus 1 plus xi by 2 into x2, 1 plus xi by 2 into x2. And what is this value? 1 minus 1 plus xi by 2. This is my, this is my two minus 1 minus xi plus 1 plus xi by 2 into x2. And what is this? This I can write as 1 minus xi, right? 1 minus xi by 2 into x1 plus 1 plus xi by 2, 1 plus xi by 2 into x2, And what is 1 minus j by 2? It is n1, right? n1 x1 plus 1 plus j by 2 is n2, so n2 x2. Or in other words, I can write it as n transpose into x1 and x2. This is my x. Okay, using the same n matrix. N is n1, n2, so n transpose is a row matrix. This, let me write it as n1, n2 times this nodal location vector x1, x2. So this equation has converted my location within any point with the same transformation matrix nt. Okay, so here this is what is called coordinate transformation. I have expressed my coordinate of a point in terms of the nodal coordinates. Now you see my coordinate transformation equation and displacement transform equation are same. My transformation matrix is same for both displacement and coordinate. Now when I have that kind of shape function, so that the same transformation applies both for displacement and also for coordinate. So displacement transformation is this and coordinate transformation is this. Therefore, since the same transformation I am applying for both displacement and coordinate transformation, so this type of elements are called isoparametric elements. This is a very commonly and famous term in finite element analysis. So this is called isoparametric element. Isoparametric element. I'm sorry, isoparametric element. And we have many advantages of defining an element as isoparametric element, because later on you will find, you remember that my element stiffness matrix is basically what? Strain displacement matrix BT into constitutive matrix into B into dV. Now when I have isoparametric elements, these integrations becomes easier, numerically easier, so computational cost will be less. Okay. Also the same transformation matrix I need to store only for once, so it will save memory also. Okay, so that's why isoparametric element is a very commonly or preferred way of defining elements. That's why we have taken up in this case an isoparametric a isoparametric element. Okay, so now let us find out the strain displacement matrix of our element. And we know that the strain displacement relation is given by epsilon, that is strain, is basically del u del x, or in this case, since it is a one-dimensional element, we can write du dx, right? And this du dx I can write now in terms of the natural coordinate du d xi times d xi dx, right, by chain rule of differentiation. Now we know that xi is equal to Now xi, we know we had defined it as 2 by x2 minus x1 times x minus x1 minus 1, right? And therefore my dxi dx, hence dxi dx is 2 by x2 minus x1, right? 2 by x2 minus x1. Also we had the displacement transformation relation, u in terms of the nodal displacements. Also we have u equal to n1 u1 plus n2 u2, and putting the values of n1 and n2, I write it as 1 minus xi by 2 is my n1 into u1 plus 1 plus xi by 2 into u2, right? And therefore what is my du dxi? Du dxi will be my minus u1 minus u1 plus u2. Yes, divided by 2, of course, so minus 1 by 2 into u1, so this whole thing divided by 2, right? From this expression, if I differentiate with respect to xi, I get minus half of u1 and plus half of u2. So therefore what is my strain now? Therefore my strain is du dxi into dxi dx, so I have u2 minus u1 by 2, that is du dxi, into dxi dx, that is 2 by x2 minus x1, which is nothing but u2 minus u1 by x2 minus x1, right? And this I will write as, in matrix notation, I will write as 1 upon x2 minus x1 into minus 1 1 into the nodal displacement vector u1 u2. All right, and this is my nothing but L, which L is my length of element, times minus 1 1 into u1 u2, and this I write in terms of strain displacement matrix as, this I can write as B transpose into D matrix, where my B is given by B is 1 upon L into this column matrix minus 1 and 1. Alright, so we have got our strain displacement matrix like this for our element. Alright, so we can write ultimately that strain is B matrix B transpose into this nodal displacement vector D. Okay, now let us find out the stresses. So stress, you remember that our basic objective in finite element formulation is we want to express all the quantities whatever possible in terms of my nodal displacements. That's why we are doing all these transformations. All right, so now stress from Hooke's law, what I get if I assume a linear elastic material, then from Hooke's law for a one-dimensional body, I know that my sigma is E times the strain. Okay, and therefore by putting the value of epsilon from here in terms of the strain displacement matrix, therefore I can write sigma as E times, E is a constant for one-dimensional element, otherwise it will be a matrix, so we'll call it constitutive matrix C, then B transpose into D, where D is my nodal displacement vector. All right, now let us use Rayleigh-Ritz method to find out the total potential of the element. Okay, so now let us find out the total potential. The total potential for a general 3D body is given by the strain energy minus the work potential, right? So I can write pi, I'm sorry, let me delete this. So pi is equal to my strain energy for the element, so half of, for a general 3D element we can write it as sigma into epsilon transpose, or sigma transpose into epsilon dV when we integrate over the volume. So this will give me the element strain energy minus the work potential due to the body force, due to the surface force, and due to the concentrated load applied at different points. Okay, for example, suppose I have a 3D body like this. Suppose I have a 3D body and say It is supported at various points, of course. And say we have discretized it with some finite elements, something like this. Say I have triangular elements we have used. Now the total potential of the element we can write as half integration of sigma into epsilon transpose when the integral is done over the volume of the element, minus this work potential. These are the work potential. This is the work potential of body forces. So if I have found out the consistent body force load vector, then d transpose into body force load vector, consistent load vector due to body force, that I need to integrate, and then d transpose into surface traction, that has to be integrated over the surface area of the element, and these are the work potential of the concentrated nodal loads whatever are there. Okay, now if I put the value of sigma as this is my value of sigma we have got, and this is my epsilon. Epsilon is b transpose times the nodal load vector, nodal displacement vector, I'm sorry. Then you know that if I have a matrix product AB, then AB transpose is given by B transpose A transpose. This is known from your matrix algebra knowledge, right? So the order of multiplication changes. So by doing that, I have put the value of sigma and then epsilon transpose. Epsilon transpose will be D transpose into B transpose transpose, which will be B. So D transpose into B, into my dV for a linear element is cross-sectional area into dx. Now what I do is I take this D transpose outside into integration of this BTEB times A dx, this integral, then multiplied by my nodal load vector, nodal displacement vector D. Okay, this is my potential energy. This whole thing is my potential energy of the element. All right, this whole thing is my capital U of the element. All right, now let us find this dx in terms of d xi. We have already got dx in terms of d xi. So for that, what I will do, I know that d xi dx, earlier we have found that we have d xi dx was my 2 by L. Remember, 2 by L. Here we can see it in earlier page. You see, d xi dx is 2 by L. x2 minus x1 is L, so 2 by L. So therefore, if I use this value, then I have dx equal to, from here I can find out dx is equal to d xi divided by 2 by L. So L by 2 into d xi. all right, and xi is varying from -1 to 1 here, we know. Okay, therefore what will be my element strain energy? So element strain energy will be from this equation. From this equation here I can write element strain energy as d transpose into, so my element strain energy I will get from here half into d transpose, so that half I should write here, half times d transpose into this integral I will write now. This integral I will write as a into dx is L by 2 d xi, so this L by 2 I will write here into I have B transpose into E into B, right, into integration of from -1 to 1 d xi. I have expressed dx equal to L by 2 d xi, and this whole thing multiplied by again d. Okay, so this will be, therefore u of the element will be half into d transpose into a L by 2 into B transpose into E into B into, this is 2, this whole thing into D. Okay, so this 2 and this 2 is cancelled, so I have half d transpose into, now I will write AE and then I'll put the value of B transpose. What was my B transpose? B transpose was -1 1 by L, so 1 upon L, right, into my B. B is -1 1 into again 1 upon L, is not it? And here I have this L I missed, so this whole thing, let me use some other bracket, say this big bracket, into D. Okay, and now I have half D transpose into, if I multiply this matrix by this matrix, what I will get? I'll get, you see, I have AEL divided by L square, so I have AE by L, and this matrix multiplication, minus 1 into minus 1 is 1, minus 1 into 1 is minus 1, then minus 1 into 1 is minus 1, and minus 1 into this is again 1. 1 into 1 is 1. So this into D. So half the displacement into the internal force. So if I have this as stiffness matrix, then I know that stiffness multiplied by the nodal displacement will give me the internal force. And therefore, obviously, from here I can write that comparing this to U element equal to half D transpose into the nodal internal force, which is K times D, we get the element stiffness matrix as K equal to A by L into this matrix 1 minus 1 minus 1 1. Okay, so this gives me the same stiffness matrix that we got earlier by using what, Galerkin's method, right? By using Galerkin's method we got the same matrix earlier. So this method also is giving me the same matrix. So this is how we can formulate the two-noded bar element by using Rayleigh-Ritz method, by using the total potential energy approach. Okay, so with this we have come to the end of this lecture. We have seen how classical Rayleigh-Ritz method can be used to approximately solve simple problems where boundary condition and the geometry is simple enough. And we have also used the two-noded bar element. We have got the we have used natural coordinate, which is a non-dimensional coordinate. We have got the value of strain displacement matrix, and also we have done the integration with the help of this natural coordinate here, and we have seen that that kind of integration is pretty easy compared to integration done over the actual coordinate. Okay, that's why we prefer natural coordinates, so that the numerical integration becomes cheaper. In complicated elements like 3D or 2D elements, if we try to do the numerical integration in terms of the absolute values of the coordinates, nodal coordinates, it will be more costly. So we use natural coordinate, and another advantage is that when we use natural coordinate, then for every element, for finding the stiffness matrix, those integrals will remain same if the element type is same. So we need to store only for once. Okay, so that will reduce the computational cost. So, and we have also seen what is called isoparametric element. In isoparametric element, we use the same transformation matrix, that means the same shape function matrix, to express coordinate within the element in terms of the nodal coordinates, and also displacement within the element in terms of the nodal displacements. When we do that, then those elements are called isoparametric elements. So with this we come to the end of this lecture. In the next lecture, we will take up the beam element, and then we will solve a few simple problems involving loading of beams, okay, maybe say fixed beam or continuous beam, etc., by using the finite element method. So with this we come to the end of this lecture. Thank you.